Hello everyone, welcome to week 8 of the course of Foundations of Cryptography. So let me share my screen. Is my screen visible?
Yes, ma'am.
Okay, thank you. So we will start with the assignment questions from week 7. So the first question was this: select the correct options from the following. A CCA secure encryption scheme necessarily implies a secure authenticated encryption scheme. So let's go one after another. So for the first statement, so you can answer whether this statement is correct or not. It says a CCA secure encryption scheme necessarily implies a secure authenticated encryption scheme. Anyone would like to answer?
Ma'am, it's wrong.
It's wrong, right? Why?
Because AE scheme needs ciphertext integrity and CCA. So CCA cannot necessarily imply AE scheme.
Correct. Absolutely correct answer. So, just a moment. Yes, so as you have correctly said that authenticated encryption scheme should have two properties. One is CCA security and another is ciphertext integrity. So if I am saying that a scheme is CCA secure, then it does not mean that scheme will satisfy ciphertext integrity also. So we cannot necessarily say that the scheme is authenticated encryption as well. So this is wrong, correct? This is wrong. Next statement says that a secure authenticated encryption scheme is necessarily CCA secure. What about this? Quickly.
This is true.
This is true, right? Obvious. If it is authenticated encryption scheme, then it has to satisfy both the properties. So of course CCA security will be satisfied. So this is true. Next statement says if an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. What about this?
Below both are wrong.
Okay. So this is wrong because if it is CPA secure, so as we already know that these security concepts with the growing power of adversary, so there comes ciphertext only attack where the adversary has the least power, then adversary power increases gradually from KPA security, then CPA security where the adversary has encryption oracle access, then CCA security where the adversary has both the encryption and decryption oracle access, and there comes AE authenticated encryption scheme where the scheme has to be secure against CCA attack, chosen ciphertext attack, and it should also satisfy the ciphertext integrity. So apart from confidentiality, integrity or authenticity is also ensured there. So here, because CPA security does not imply CCA security and CCA security does not imply AE security, that's why this statement is wrong. Okay. And last statement is it is impossible for an adversary to forge a valid tag with a non-zero probability when a secure message authentication scheme is used. So this is wrong as you have already answered. So why? Because we already saw that there is always some non-negligible probability. So it's saying that it is impossible, but the truth is that yes, it is possible for an adversary to forge a valid tag even if the MAC scheme is secure, but it can be able to forge a valid tag with some negligible probability, right? So that is non-zero probability. We saw about information theoretic secure MAC, right? Or there we saw that even if the adversary is allowed to have unbounded computational power, then also for information theoretic secure MAC, the adversary should be able to win, like should not be able to win except with negligible probability. So there we emphasized upon the fact that the scheme should remain secure even in presence of computationally unbounded adversary, but we allowed some negligible probability of winning there. So it's not zero probability of winning, right? So there is always a very small, that is negligible amount of chance of winning for the adversary in case of message authentication scheme or MAC scheme. Okay, so as you have rightly said that this is also wrong. Okay, so only
Ma'am, I had a question regarding one-way function and one-way trapdoor function. Can I ask that?
okay, yes.
Ma'am, as we know that in one-way trapdoor function, we have a secret key which is used for the inversion purpose, which makes it easy the inversion purpose, as it is hard to invert in the one-way function. So, ma'am, I just wanted to ask, does this secret key make the security of the one-way trapdoor function more high than the one-way function, or it has the same security as a one-way function?
No, security is same, I should say, because it is so why we are considering the trapdoor thing actually. So let me put it this way, that one-way function property which says that you take a random element from the domain, it is easy to compute. So x is some element from the domain, it is always easy for any arbitrary x, it is always easy to compute f of x and go to the range y. But given some given some random element y in the range, coming back is hard, right? This is the concept of one-way function. Now this essentially helps us to build some crypto primitive depending on the hardness of this backward computation, right? Now why do we then need the trap? Like we are defining another primitive, right? So one-way function is a cryptographic assumption, right? Where we assume that if one-way function exists, then these things can be built upon, like PRA, PRG, symmetric cryptography, and so on. And then we say that if we define another cryptographic thing, that is one-way trapdoor function, and we say that there is some trapdoor information that you can also say it's a secret key, whatever. So trapdoor is hidden from an adversary, right? As it is done with the secret key for an encryption scheme. So trapdoor is some hidden information. It is known only to some genuine, like whom we want to learn the backward computation. So for this you cannot use this thing because it is always hard to compute, right? There is no way to get back once you reach here, right? Also so what I am trying to say is that in one-way function, you pick any random element from the range, it is always hard to get back to the domain part, right? So if you want to design some scheme where you want that this part remains hard, that's okay, but for certain entities, some authorized entities, you want them to learn the backward computation, right? Result of the backward computation. Then you want some helper information that we call trapdoor, with the help of which they are able to get back. So those are authorized entity, I can say, whom we want to learn the result of backward computation, that is given y to learn the x, and that may help them to build some other crypto primitives. So trapdoor is a secret information. It is not known to everyone. It is known only to certain entities whom we want to learn the backward computation. So the trapdoor thing does not reduce the security of the function. It still has the property of one-wayness from the viewpoint of from the viewpoint of security, because it is still hard to get back from here to here. Why? Because we assume that the information of trapdoor is not known to everyone. Only with the help of trapdoor it is easy to come backward. So, am I clear?
Yes, ma'am.
Okay. Thank you. Okay. So maybe we can proceed to the next question. Let pi so pi consists of three tuples of algorithms: Jane encrypts keygen encryption and decryption, B symmetric key encryption scheme with message space and ciphertext space M and C, which is L-bit binary string, both message space and ciphertext space. And then we consider a variant pi dash, where it is the three tuples. Keygen is exactly the same as in pi, and encryption and decryption algorithms are modified. How? So here we are saying that ciphertext space is actually L plus 1 bit length binary string. Message space is also. So both message space and ciphertext space are now L plus 1 bit. So M is same, message space is same. So previously message space was 01 to the power L. Here message space still remains same, but ciphertext space was previously L bit binary string, but now it has become C dash, which is L plus 1 bit binary string. And we define the encryption in this manner. Given a L bit length binary string, we first apply the normal encryption algorithm on the same message M with the key k. So this is the encryption algorithm as defined in original scheme pi, and then we concatenate a single 0 bit. And in the decryption, modified decryption, what we do is that we just ignore the last bit, which is the 0 bit, and we do run the normal decryption algorithm, that is the decryption algorithm for scheme pi, on the first L bits of the ciphertext. So that is how encryption and decryption is run in the modified pi dash scheme. Now there are comments about the security of this scheme. So it says, first option says that pi dash is not CCA secure even if pi is CCA secure. I think this question was maybe discussed last week also. So let us just quickly recapitulate. So anyone would like to answer CCA security part? If pi is CCA secure, then pi dash is not CCA secure. This is true or false, and why? Anyone can answer. Praveen is writing, ma'am, I just wanted to know what percentage of questions will be there from the assignments in the final exam, and can you please help us with few model questions we are finding? Praveen, actually the fact is that the PMRFTS has nothing to do with the question setting part, right? We also get to see the question on the NPTEL website, the weekly assignments also I am talking about. They are also, we get to know them after they get posted on the website. So we really have nothing to coordinate with the actual question setter. Okay, so what in the exam, what questions or how, I think if you understand the assignment questions that are getting discussed, and if you go through the lectures thoroughly, get to know the concepts uh, well, then it should not be much problem to clear the exam, I believe. So I really don't know what, like, it should be helpful because of course there will be some link with the assignment question, otherwise why would they keep this weekly assignment thing? That the whole purpose is to get you acquainted with kind of questions you are going to face in the final exam. So they, of course there will be similarity, they will not be exactly the same, but there will be similarity if you I don't say practice, but if you get to know the concepts well, understand the questions answers that are discussed in the tutorial sessions, and of course the main thing is go through the actual lectures, that will be actually helpful. So get through the main lectures by professor and take help from the tutorial sessions that are happening weekly twice by some other TA also. I think that should be helpful. Okay. Okay. Coming back to question 2. So anyone would like to answer about CCA security of the modified PIDA scheme? And also I think I can mention another thing is that Praveen, like before the final exam, so we will get basically I guess 13 weeks. Okay, so this is week 8 going on. We will have 5 more sessions, and in the last session I will try to summarize. So we will get a 2-hour session, right? So I will try to summarize the whole syllabus maybe in the last session before the final exam. But before that, try to go through the lectures, and then if you have doubt in some particular portion, then we can discuss in that last session actually. And also the current topics that we are discussing every week, then also you can if you have particular doubts, you can always ask. Okay. So I think, okay, about the CCA security, let's get back to that. So basically, if even if pi is CCA secure, pi dash will not be CCA secure. The reason being that so we can basically do an attack by exploiting the decryption oracle service of pi dash. How? So let's say, then let's draw this challenger and adversary, and in the challenge phase adversary has queried with 2 message of its choice, as it is always done, right, in the encryption scheme security game. And the challenger has replied with a challenge ciphertext CB, right, which is encryption of any one of them. Now CB has this form, right, which is encryption of MB under the key K appended with a single 0 bit. So what adversary now can do? Simple. Anyone would like to answer at this point how adversary can change the ciphertext so that it can learn the underlying plain text MB? What should be the decryption oracle query from the adversary side? Am I audible, by the way? Okay. So you would like to answer what should be the decryption query, decryption oracle query? So whenever we talk about breaking the CCA security, yes. Okay, I thought anyone has unmuted himself or herself. Okay, so whenever we talk about breaking the CCA security, what we do is that we change the challenge ciphertext in a way that it gets decrypted to a message which has some relation with the actual underlying message. So here we can do this. So we construct CB dash the ciphertext to be, so this part, the first k bit, first L bit, so ciphertext is L plus 1 bit, right? First L bits come from the encryption of the scheme pi. So this part remains as it is. You keep the first L bits as it is, and you just change the last bit, last 0 bit to a 1. So this 0 is flipped to 1. Now this, as a whole, this ciphertext is different from the challenge ciphertext. So the adversary is allowed to query with a ciphertext which is different from a challenge ciphertext, right? Now when this ciphertext goes to the decryption oracle, the decryption oracle replies with what? So decryption in pi dash works in this manner, right? It just discards the last bit, so it does not care about the last bit. It just takes the first L bit and decrypt it according to the scheme pi. So it runs decryption of the first part. So this is nothing but this. So it will return MB. So the adversary can see the exact value of MB by this mechanism, and security is gone because the adversary knows which message among M0 and M1 got encrypted by the challenge ciphertext. So it is not CCA secure, right? Okay. Second statement says that if pi is multi-message COA secure, then pi dash is multi-message COA secure. Ciphertext only attack they are talking about. So what about this COA security? No? Anyone? Okay, so this statement, yes,
should be true.
it is true, yes.
It should be true, but I don't. Yeah.
Yes, it is true. You have any other doubt? Okay, so it is true. This was true, right? Not CCA secure. This is also true. Why? Because just note that if pi dash is not COA secure, so what we get to see in the COA game is that we get to see only the ciphertext. So you get to see this form of ciphertext being communicated from a sender to receiver, and the adversary's job is to guess some information about the plain text message distribution. Now if you are saying that in the modified scheme, here by looking at this form of ciphertext you are able to gather information about the distribution of underlying message, then you can obviously recover the same information about the distribution of underlying message from this kind of ciphertext as well, because the only difference is some extra 0 bit appended at the last. So this really has no information about the underlying message. This part of the ciphertext is a redundant part. So you have to utilize the information of this part only in order to gain some information about the message. Now if in the pi dash scheme you are saying that by looking at the ciphertext, in the ciphertext only attack scenario, you gain some meaningful information about the underlying distribution of the plain text, then you must be able to retrieve the same amount of information by looking at the ciphertext of the scheme pi, but pi is already given to be multi-message COA secure. Okay, I have written only a single ciphertext here, but the scenario will not change even if I write multi-message encryption, right? So there will be a vector of ciphertext then, right? Encryption k of m1 appended with 0, encryption k of m2 appended with 0, like that, say L number of message encrypted together with the same key, right, in the scenario of multi-message COA security. But then also the argument remains the same, that if pi dash is not COA secure, then that will imply that pi is also not COA secure. However, pi is known to be multi-message COA secure, so by contradiction we conclude that pi dash is multi-message COA secure. Okay. If pi is CPA secure, pi dash is CPA secure. So by the similar kind of argument, this is also a true statement, because in case of CPA security, the adversary is given access to the encryption oracle, and as I already mentioned, that encryption looks like this in the modified scheme, just encryption of the original scheme appended with a extra 0, and extra 0 does not really contain any information about the underlying message. So this is a redundant part of the ciphertext. It gives no information absolutely about the underlying message. So if by exploiting the encryption oracle service, the adversary is able to gain meaningful information about the underlying message of challenge ciphertext in the pi dash scheme, then it should also be do the same in pi scheme. But pi is already given to be CPA secure, so with the same similar argument, by contradiction we can say pi dash is also CPA secure. And because in the first statement we already told that if pi is CCA secure, that does not imply pi dash is CCA secure, so this statement is of course wrong. It is just the opposite statement of the first statement. Okay. So next question, select the incorrect options. So first statement says that deterministic MAC cannot be used in the construction of secure authenticated encryption scheme. Okay, anyone? So as you have seen in the lecture, that in the construction of secure authenticated encryption scheme, there are essentially three approaches. One is encrypt, then authenticate, another is encrypt and authenticate, and another is authenticate then encrypt. Okay, so MAC comes in this authentication part. So it is saying that deterministic MAC cannot be used in the construction of secure authenticated encryption scheme. So anyone, is this statement correct? Not? You can unmute yourself and speak, or you can write in the chat box also. You are saying false. Right, this statement is false. Actually, deterministic MAC can be used in the construction of secure authentication scheme. You may have already seen that in encryption then authenticate approach, we actually take a CPA secure encryption scheme, right? CPA secure encryption scheme and a SCMA secure MAC, and these two combined in encrypt then authenticate approach actually leads to a authenticated encryption scheme. And SCMA security boils down to CMA security in case of deterministic MAC. So yes, it is possible to use deterministic MAC in the construction of secure authenticated scheme. So this statement is wrong. To break the security of a cryptographic construction which is probably secure in the random oracle model, one must discover a weakness in the actual hash function. What about this statement? True, false? Quick answer from any one of you.
This is false because this is false.
Why?
This is false
But
because in provably secure ROM model we don't. Hello.
I am
Am I
listening.
audible?
Yes, you are audible. Yes, you are audible.
Because in provably secure ROM model, the the internals of the hash functions are not known.
Acha, by that logic, you were saying that. So here the point is that I understand your thought, but the answer is actually it is true. I am explaining why. So what you are saying is that the internal function of hash function is not known. That is the assumption. When we are assuming or modeling the hash function as a random oracle. So in real world, whenever some library or something is providing you with some particular hash function, the algorithm is never really secret algorithm, right? The hash function will have a certain deterministic algorithm and that will be publicly known, right? It will be some public library that is providing the hash function. Remember this for utilizing the hash function as a random oracle, we assume that the internal functionality of the random oracle, which is the hash function here, hash function is being modeled as a random oracle. We assume that the internal functionality of the random oracle or the hash function is not known. That is our assumption. But in real world, when we are trying to cryptanalyze of a system that is provably secure in the random oracle model and uses some particular instantiation of hash function for implementing that provably secure system, then actually you would like to analyze the hash function. The algorithm will not be hidden in real world. It will be a public algorithm, and if you are able to find out some vulnerability such that it is not a proper choice which which scatters its output to uniform random distribution of the output space, then it is not a suitable choice of hash function which should be modeled as random oracle. So it is provably secured with the assumption that the internal functionality of the hash function is not known and the hash function outputs are in this manner that given an input, its output should be uniformly distributed over the output space. But whether that condition is really satisfied by that hash function, that you need to ensure. So not all functions are suitable candidate to get it instantiated with a random oracle model. Okay, so this statement is true. Am I clear?
Yes, ma'am.
Okay, so this is true. There does not exist any ROM, random oracle model based crypto primitive, that is efficient and highly secure. What about this statement? Okay, this is actually false because as I already said that if you are instantiating your implementation with a suitable hash function which is able to be considered as a random oracle, then okay, your scheme will remain secure and due to this random oracle model thing, usually implementations becomes quite efficient than the standard model. So it is not true. There can exist ROM based crypto primitive which are efficient and highly secure at the same time. Yes.
Ma'am, one question here.
Hmm?
Ma'am, one question here. How can we say that if it is ROM based crypto primitive, then it is both efficient and highly secure?
How can we say?
Secure we cannot say if it is ROM based because
it is
We cannot. There
high.
doesn't exist.
The term highly is a vague term here. So
But it's
what
not.
basically it is a very informal statement. I agree with you. We deal with either it is secure or not secure. We talk about provable security. So provably secure in random oracle model it is possible, but highly this term is really confusing. That I agree. Like, what do you mean by highly secure? In cryptography we talk about it is secure or it is not secure in with respect to some specific attack model.
When
Yes.
we say, what I understood from the question was, when we say it is highly secure, it means it's being proved publicly. I,
What do you mean by proved
that
publicly?
is what I understood. So
What do you mean by
because
proved
ROM based is
publicly?
when the
Hmm?
publicly means when the when its internals are being given to the public. But when we say it is ROM based, then ROM based
No, no. So the
primitive, then it means
so there is clear gap between a theoretical construction and a practical construction. Okay, in theoretical construction we assume a random oracle model. We do not really specify how are we going to uh, um, how are we going to realize that random oracle model. That we don't specify in theoretical construction. We just say that we assume there is some random oracle model, and assuming the existence of random oracle I am giving the security proof of some construction. That is the theory part done. Now when I am going to implement that construction and deploy it in the real world, I have to realize the random oracle by some means, and hash function is a, promising candidate for realizing random oracle. But as I already mentioned that not all hash functions are suitable for that. You have to have a very rigorous check on the hash function whether it is suitable to be used as a random oracle service. Once that test is passed, so there can be several analysis performed on the hash function behavior, and if the hash function behavior is found to be suitable so that that hash function can be modeled as random oracle, then you are safe to use that hash function in your practically implemented crypto construction and get a secure construction in random oracle model where the random oracle has been realized by a hash function tested, right? That hash function is suitable for being used as random oracle. Random oracle is an abstract thing. Okay, so absolute random oracle you cannot construct, just like truly random function you cannot construct truly random oracle model, but you find out some way to realize that behavior of random oracle, and to realize that you can use some hash function but not all hash functions are suitable candidate for that. You have to check that and then use that in your practical implementation. So there is nothing called as publicly secure. Everything is public whenever you are, apart from secret key or anything that is mentioned as secret in a crypto primitive. Apart from that, everything is public. Okay, but the assumption is that when even after you know the public algorithm of the hash function, still your output of the hash function, when you don't see the output really, the input really, the output of the hash function should be scattered in a uniform random manner on the output space. If that property is satisfied by the hash function, then it is okay to use in practical implementation. Okay. Okay. In a secure authenticated encryption scheme, the decryption oracle does not provide any advantage to the adversary. Okay, this is okay, so they are talking about secure authenticated encryption scheme. So if it is a secure authenticated encryption scheme, then it is already CCA secure. So if it is CCA secure, then of course yes, decryption oracle should not provide any advantage to the adversary, right? So incorrect statement are the first one and the third one, right? Okay. So what about this question? Honest receiver, corrupt sender. Someone just may quickly type in the chat. I will wait for your answer. Just give me 2 minutes. I will come. You can just put your answer in the chat box in the meantime. Okay. Just give me 2 minutes. Okay, there are, I can see there are 2 answers. No, more than that, I think. Okay, 3 answers. Third option everyone is saying. Okay, let me check. Yes, third one is the correct answer. So just to quickly recapitulate, honest receiver, corrupt sender. So that is if sender is corrupt, it may try to first in the committing phase it can commit the message M, and while in the opening phase it can claim that it sent the commitment of some other message M dash. That is what corrupt sender may intend to do, and to prevent that we have the binding property. So 1 maps to 1 on the right hand side. Receiver, there are 2 options: provides opening information or accept or reject data M. Very clear, sender's job is to provide opening information, and receiver accepts or rejects a data M based on the fact that whether the the opening thing works properly. The opening information provided by the sender is leading to valid data. So okay, so 2 maps to 3, 4 maps to 2, and the rest is honest sender, corrupt receiver. Of course, if the receiver is corrupt, then it may try to distinguish between whether it is what is the so it may try to gain information about the underlying message M without having the opening information about some commitment, and in order to prevent that we have hiding property. So 3 maps to 4. Okay, so next question, select the correct options from the following. Binding property of hash function based commitment schemes relies on the collision resistant property of the hash function. So okay, quickly you can write in the chat, is it true or false? Does collision resistance property suffices to ensure binding property of a hash function commitment scheme? BD, she is saying correct options. So you are saying this is wrong. Relies on okay, the binding property, I think it just relies on the collision resistance property of the hash function. For the hiding property, we need, apart from collision resistance, we need the hash function to be modeled as random oracle for the hiding property. But for the binding property, it should suffice to rely on collision resistance property of the hash function. So first statement is correct. About the B Merkle tree to store 1024 unique elements, we will have a total of this node. Okay, so this is also true. So quickly with a small example, so let's say if 4 unique elements are there, so they constitute the leaf elements of the tree. Then you store the hash of left child, hash of right child here. Here also another node containing hash of its left child and right child, and these two will have their own hash node, right, containing the hash of left child and containing the hash of right child, and there is the head pointer of the or root pointer of the tree. So there are 1 2 3 4 5 6 7 nodes for 4 leaf elements. So 4 is 2 to the power 2. You can see that 7 is nothing but 2 to the power 3 minus 1. So similarly, if there are 1024, that is 2 to the power 10 leaf nodes in the tree, then we will have total 2 to the power 11 minus 1 nodes in the whole tree, right? Okay, so this is true. Modifying a leaf node in a Merkle tree will result in order of k changes to a tree of depth k. This is also true, right? Because whenever you change, so let's take this example, this tree has a depth of 2. So whenever you are changing, let's say this data node, then this will affect the hash of the right part of this node, and overall the content of this node will change, and that will affect the content of this node, this hash value in this node. So you need to change 2 hash values in order to accommodate this change in this node. So if you have tree of depth k, then you need order of k changes in the Merkle tree along the path from root to that particular leaf node where the change is occurring. This is also correct. Last statement says that receiver in hash function based commitment schemes is allowed to make polynomial number of calls to the random oracle. So yeah, as long as the receiver is a polynomial time entity, so it can make polynomial number of calls, and calls to random oracle by each party, they are done in a private channel, as you know. So yes, it can vary, right? So
Ma'am, in this, yeah, this Merkle tree, I got it wrong. Merkle tree to store 1024. In the assignment also, it's mentioned that only three are correct.
Okay, I see that in the answers also only three are
Okay.
correct. Okay. Mm-hmm. So, okay, I think I should take a look at that. Do you have an answer? So, hello?
And in the solution, the answer was given as 2 to the power 11.
Okay. Okay, so, okay. I guess, okay, I think I missed this fact. So, let's hear. So, there are these two values, right? So, there will be another root node that will store the hash of both of these two. I think I missed that. So the Merkle tree structure is this. So four nodes, they are data node. In the hash node, this part stores the hash of content of this left child. This is the hash of content of this right child. This is the hash of this left child. This is the hash of this right child. Now here, this is the hash of the whole content of this. This is the hash of whole content of this. And then the final root node is the hash of the whole content of this node. Okay, so that is how it makes it 8, right? 1 2 3 4 5 6 7 8 to the power 3. I think I missed the last node, which so finally you have to have a final hash of all the content. So these two hashes are different for two child, left child and right child, and final hash should be the hash of the content of both these hashes. I think this is clear, right? So with the same logic, uh, for 2 to the power 10 leaf nodes, you should have 2 to the power 11 nodes in the Merkle tree. Does that make sense?
Yes.
Okay.
So it means we are not considering the root node.
Where? So this is the final node, right?
In this answer, we are not.
Mm.
Which one, ma'am?
So the answer is 2 to the power 11, right?
Yes.
Here, here
So we are not
we are considering the final root node. That is why the count increased. Uh, can you just make it clear where exactly the doubt is? So four data nodes are there. These two are hash nodes, like nodes storing the hash values of their respective left and right child data node. Then this is another node storing the hash value of the left content of this whole left node, and content this stores the hash of the content of this whole right node. And these are two different hash values coming from the left and right child of this node. So the final node will store the hash of both these two nodes. So this one we are also considering. So 1 2 3 4 5 6 7 8. That is 2 power 3 nodes for 2 power 2 leaf nodes.
but then in this answer, it is 2 raised to 3 minus 1 nodes, right?
So that makes it incorrect
We have
actually.
4 data nodes.
So that is why it is incorrect. So previously I said it wrong. I said this is correct, but as you have correctly pointed out that in the
No,
answer
but
side.
this is correct. This is correct actually. This is correct. That is what my question is, that I also marked this to be correct, because by calculation, if we have 2 raised to the 1024 unique elements,
Mhm.
then total nodes are 2 raised to 11 minus 1. That is what
Hmm.
it is not two. The answer that the 4 leaf node that you are giving an example.
Mm-hmm.
So in this also, the number of nodes that are coming is 2 raised to power 3 minus 1.
But
So
I what
7 nodes are coming, right?
but here the forget this scenario. There here in the left hand side, here the count is 8. When we consider the final hash of this node, that is another node, this hash value.
Where I do not get this. The final, where is
Mhm.
the final node? Final is a root node, right? That we have already considered.
What I am saying
That's
is
the
that
hash of all the below values of.
uh, in this particular node there are two hashes, this side and this side. I am again applying another hash on the value, concatenating these two hash value, and that final value I am storing in another node. Maybe let us proceed. So maybe we can again discuss this in the next session. What I understood is that so they are considering the answer to be 2 to the power 11, right? Okay, I think let us proceed to this week's topics. Okay, so choose the right options for the authenticate then encryption approach, which is instantiated with the CPA secure encryption scheme and SCMA secure MAC. So this is very like objective type of question. Maybe you can quickly answer this. Anyone? Okay, so in the authenticate then encrypt approach, what happens is that if the final encryption scheme, right, if that is CPA secure, so we are talking about authenticate then encrypt. So what happens, let's say we have the message M and we have authentication key KM and encryption key KE sampled independently from the max key space and encryption key space respectively. Then we first authenticate, right, with the authentication key and whatever the, so let's denote it with T, the tag, and then what we do is that we apply the encryption scheme under the encryption key KE on this, right, the tag concatenated with the message. Now the final ciphertext that you see is simply an CPA secure encryption on M concatenated with T. Now, as you know, for authenticated encryption scheme, it is required that the encryption should be CCA secure. But here you are using a CPA secure encryption scheme at the final phase, so that does not really. So it may be the case that the encryption scheme that you are using, it is CPA secure but not CCA secure. In that case, your authenticate then encrypt approach will fail as to give the authenticated encryption scheme. Okay. For example, I think in the lecture it is given that for CBC mode of encryption, CBC mode of block cipher encryption scheme, if you use, then it is CPA secure, of course, but like exploiting the padding oracle, you can actually learn the underlying message, and that kind of attack is possible here also, to recover the underlying M concatenated with T in its whole, and then the CCA security is broken. So that is why we can say that it may not even be CCA secure, and it may not be authenticated encryption scheme. Also, ciphertext integrity. So what is ciphertext integrity basically? So once you see the ciphertext corresponding to various messages, so for a set of messages, the adversary sees the set of ciphertext, right? And then its job is to come up with a new ciphertext C star, which has valid decryption such that its decryption is not among these MIs, right? So it should be a valid encryption of some new message, right? So here, as you can see, that it will not actually provide ciphertext integrity, because it is hard to come up with once you have ciphertext of this form, right? Encryption of KE MI TI. This is how your ciphertext is created. Now what can you do is that let's say so if you are using some deterministic MAC, you can actually, I'm just thinking how you can create some other C star such that it becomes ciphertext of some valid M star and corresponding T star, right? So anyone would like to comment on this, how the ciphertext integrity is not there here? sorry for the background noise actually. Okay. Yeah. Okay. So this scheme, it says that it does not provide ciphertext integrity. I think let us get back to this question later. As already mentioned that it is not CCA secure, and hence it is not also an authenticated encryption scheme. About the ciphertext integrity property, so we will just come back. Okay. In the key exchange problem, the goal of the sender and receiver is to agree upon a common public key over a private channel, agree upon a fixed common key over a public channel, agree upon a fixed common key over a private channel, agree upon a random common key over a public channel. So, anyone in the chat? In the key exchange problem, what is the output of the key exchange protocol? Of course, the key exchange happens in a public channel. That is evident, right? It will be over the public channel. And so what do we mean by agreeing upon a common key? So is it a fixed common key or a random common key among B and D? It should be random common key, right? So every time, right, random common key over a public channel. Every time you run the key exchange problem, you will get a random common key. Different key, that is why it is random. It should not be fixed. Okay. Here is another question. Let sender and receiver have a pre-shared random AES key K. Then consider the following method of authenticating messages of size, which is multiple of 64 bits, to authenticate a message M with so at max L number of blocks, with each block containing 64 bits. So that is how your message space is defined. Now you are authenticating this message having L blocks or upper bounded by L blocks, each of size 64 bits. The tag generation algorithm outputs the tag. So for each of the block MI, there will be a tag TI, where TI is AES of MI concatenated with L. So this L inside angular bracket denotes the 64-bit integer representation of the integer L. That is the number of blocks in M. Okay. Accordingly, the tag verification algorithm performs the corresponding verification steps. Identify the false statements from the following. So there is comments in the option about whether the MAC is randomized or deterministic, and whether it is CMA secure, SCMA secure, and whether it should be used in encrypt then authenticate approach or encrypt and authenticate approach. So this is where we should focus. This is the tag generation algorithm. So let's first see that whether this MAC is randomized or deterministic. So for the same message, does the tag generation algorithm outputs different tag every time, or it is always deterministic? So it is deterministic, right? Because for a fixed message, let's say M1, M2, M3, you will always have the tag T1 as AES of M1 concatenated with integer 64-bit integer representation of the value 3. That is the length of your message, right? Number of message blocks. M2 will always map to the tag AES M2 concatenated with 3. Same goes for M3. So it is deterministic. Now, as you know, for deterministic MAC, we want to ensure CMA security only, because that would only imply SCMA security for a deterministic MAC. So does this satisfy the CMA security thing? So consider if we can constitute valid message tag pair for an unseen message. Anyone? Is it a CMA secure MAC if this tag generation algorithm is defined in this manner? Okay, let's say there are two message blocks. Let's say this is your message, right? M1, M2, two message blocks are present. So L is 2 here. Now also consider another message, say M dash, which is like this, M1 dash, M2 dash. Here also L equal to 2. And you query, so in the CMA game you can query with a set of messages. You get to see set of corresponding tags, and then you have to come up with, like the adversary has to come up with a valid message tag pair, right? So in this case, if you if the adversary queries with this kind of message, the tag it gets is that t equal to AES of M1 concatenated with 2, comma AES of M2 concatenated with 2, and T dash corresponding to this message is AES of M1 dash concatenated with 2 and AES of M2 dash concatenated with 2. Now you can come up with another valid message tag pair where M star is M1 comma M2 dash, such that T star is your AES M1 2, this is M2 2. You can even do this actually, even after seeing the single message, you can actually do this. You see the tag corresponding to M equal to M1 M2, then you can actually return M star equal to M2 comma M1, M star equal to M2 comma M1, and T star equal to just reverse of this. So you already know AES of M2 concatenated with 2 and AES of M1 concatenated with 2. You just reverse the first half and second half of the tag. This also works even with a single query. So, okay. So basically this is not CMA secure, right? And then it is saying that if MAC is not itself secure, then it should not be used anywhere, right? Whether be it encrypt then authenticate approach, encrypt and authenticate approach, in anything, if MAC is not secure, then there is no question of using that MAC in any further construction, right? Consider a secure PRF FK that maps n-bit binary string to n-bit binary string, using which we construct a keyed function f dash from 2n-bit binary string to 2n-bit binary string. Now fk dash x1 concatenated with x2 is equal to fk x1 concatenated with fk of x2, and x is x1 concatenated with x2. Okay. So I think I should wait for your comment on the security of f dash as a PRF, whether it is a secure PRF or not. So this goes back to the question on PRFs actually. It really has not much to do with construction of MAC or something. Like, if you see that it is not secure, then it anyway does not lead to a secure MAC. So is it a secure MAC? Quickly, we discussed this kind of questions while discussing PRFs. Anyone? How you can query with some input and see the output, and then from that output you can determine whether you are interacting with a pseudo random function. function or a truly random function. Arpana, anyone would like to answer? Okay, so as usual, let's say there is challenger, there is adversary. Adversary queries the challenger first with x1 concatenated with x2, but it gets to see as a if it is interacting with a peer if it gets this, right? This. Then it queries with x3, x4, let's say, and it sees this as if it is interacting with a PRF. Now it tries this query x1, x4. Now if it is actually interacting with a PRF, what it is supposed to see is that this and this, and note that this value you should match with the first half and this value you should match with the second half, and if you find the match for both the halves, then you conclude that, or the adversary concludes that, okay, I am interacting with a PRF. Otherwise it will say it is interacting with a TRF, and we can show that with non-negligible probability this distinguishing is possible. So it is not a secured PRF, and since it is not a secured PRF, then it should not be used in constructing CMA secure MAC. So function f dash when used directly does not lead to a CMA secure MAC. Okay. Consider the following key exchange protocol. So it is talking about some key exchange protocol. There is this Alice, there is this Bob. So Alice chooses K and R uniformly at random from n-bit binary space, right? And sends S equal to K XOR with R to Bob. Bob chooses uniform T, so it now chooses a uniform random binary string, n-bit binary string again, and it communicates S XOR with T. Alice sends W equal to, so this is U and now this is W, this U XOR with R. W is sent to Bob. Now Alice computes K, Alice outputs K, so K was chosen by Alice only, so Alice already knows K, and Bob outputs W XOR with T as the key. Now we have to check for the correctness whether K dash is equal to K or not, because at the end of the key exchange protocol both the parties should have the same key, right? So what is K dash? So K dash is W XOR with T, W is U XOR with R, XOR with T. What is U? U is S XOR with T, XOR with R, XOR with T. This XOR gets cancelled, left with S XOR with R. What is S? S is K XOR with R, so with R, K gets cancelled. So K dash is indeed equal to K, so we can say yes, Alice and Bob outputs the same key. And what about the security of the scheme? Now you can notice, so this S, U and W, they are getting communicated from one end to another, so they are visible publicly to anyone, any adversary. So they constitute the transcript of this key exchange protocol. Now if somehow from these three information you can retrieve back the exact value of key k, then your scheme is not secure, because an adversary in a key exchange protocol is not supposed to know the value of the secret by seeing the transcript. So that is the weak privacy for a key exchange protocol. And when we go for the strong privacy for a key exchange protocol, then we say that the output of the key exchange protocol, that is the value of the key, should be indistinguishable from a uniform random value over the key space. So anyway, here we have to just see whether we can retrieve back the value of key k from these three values in the transcript. So you can just see here that if you perform S XOR with U XOR with W, this gives S is K XOR with R, U is S XOR with T, that is S is again K XOR with R XOR with T. What is W? W is U XOR with R. And what is U? U is this whole thing, that is K XOR with R XOR with T, and then this XOR with R. So there are R cancelled out here, these two R's gets cancelled out, 2 is cancelled out. We are left with only single key K. So K is clearly retrievable from this transcript. So we can say that this particular key exchange protocol defined here is not a secure one. Is this clear? Okay. Which of the following is correct? Encrypt then authenticate approach with underlying secure encryption scheme and secure MAC always lead to secure authenticated encryption scheme. Is this true about encrypt then authenticate approach? You have a secure encryption scheme and you have a secure MAC. This is always true, right? You can follow in the lecture that with CPA secure encryption scheme and a CMA secure MAC, we can get a secure authenticated encryption scheme. About encrypt then authenticate approach with underlying secure encryption scheme and secure MAC actually does not lead to secure authenticated encryption scheme always, because although your encryption scheme is CPA secure, that makes the ciphertext randomized, right? CPA secure encryption scheme, CPA secure stateless encryption schemes are always randomized, as you know. So M does not always map to same ciphertext C. However, if you have a deterministic tag, so although your so in encrypt and authenticate, you use the encryption key to encrypt the message M, and you use the MAC key to compute the tag on the message M only. So although this part is randomized due to CPU secure encryption scheme, this part can be deterministic if the underlying MAC is a deterministic MAC. Although it can be secure, but it is a deterministic thing. So overall the ciphertext has some part in it which is not randomized, and we can exploit that fact to get to know what is the underlying plain text for a challenge ciphertext, right? So yes, this is hence incorrect. Authenticate then encrypt approach with underlying secure encryption scheme and secure MAC. This also does not always lead to secure encryption scheme. So this one we were already discussing that for example for CBC secure mode of encryption, that is a CPA secure encryption scheme, but exploiting the, so if there is vulnerability of the final encryption scheme, then that can be exploited in breaking the security of the authenticated encryption scheme as well. So that's why this is not true. So pi CPA is CPA secure encryption scheme over message space M CPA, key space K CPA and ciphertext space C CPA, and pi MAC is a secure MAC over message space M MAC, key space K MAC and tag space T MAC. A scheme pi 1 is composed from them using encrypt then authenticate approach. Another scheme pi 2 is composed from them using an encrypt and authenticate approach. And scheme pi 3 is composed from them using authenticate then encrypt approach. Which of the following statements are correct? So you have comments on the key space, message space, tag space for the corresponding MAC and encryption scheme, and right. So just take 2 minutes and maybe write the answers in the chat. This is just a comment on the ciphertext space and tag space. The input that is taken for the encryption scheme and input that is taken for the MAC scheme. Okay, so I think I should discuss this. All of the pi 1, pi 2, pi 3 have keys of the form k1, k2 such that k1 belongs to k CPA and k2 belongs to k MAC. Okay, this is true, right? So for the CPA scheme, encryption scheme, you independently choose the encryption key from the corresponding key space, and for the MAC scheme also you choose the corresponding MAC key from the key space of the corresponding MAC scheme. So this is true. Pi 1 has message space, so pi 1 is encrypt then authenticate, right? So pi 1 is encrypt then authenticate. In that case your first encryption is done, right? So encryption is done first, and then you apply the authentication on this ciphertext, right? And then you give this, the ciphertext, comma. I should ideally write not encryption inside this. This can have wrong implication. So first you determine the C for M, and then you apply MAC on C, right? This is the ciphertext space. So message space is M only, that is the MCPA, okay? And ciphertext space is, as you can see, this is the ciphertext space for scheme, for the CPA secure scheme. So that is CCPA, and cross the output, the tag space for the MAC scheme. So this is this. also the for the MAC space, the input space is the ciphertext space of the CPS scheme, because we are taking the ciphertext as the input of the MAC scheme. So ciphertext space for this C, that is C CPA, is actually the input space for the MAC scheme. That is why input space of the MAC scheme is ciphertext space of the CPA scheme. Pi2 has message space MCPA and ciphertext space CCPA cross. Okay, so Pi2 is encrypt and authenticate, right? So you encrypt and you authenticate. This is your ciphertext. So for the ciphertext, M is the input, so MCPA is the input space for the encryption scheme, and for the MAC scheme also the input space is the same. So for the MAC scheme also the input space is the same as the encryption scheme, and the ciphertext space is the ciphertext space of the encryption scheme and the tag space of the MAC scheme. So this is this only. There are two parts, right? And for the last option, Pi3 has message space MMAC and ciphertext space CCPA. So Pi3 is the authenticate then encrypt approach. So you first run the authentication on the message. This is T, and then you concatenate it, and then you apply encryption, right? So here you can see that the message space for the encryption scheme is actually concatenation of the actual message, that is MCPA, concatenated with the tag, right? So you can see here for the encryption scheme the message space is MMAC. MMAC is nothing but the input space here, concatenated with tag space, the output space of the MAC algorithm. So that is why MCPA is actually MMAC cross TMAC, right? MMAC is fixed, and ciphertext space, so it is nothing but the ciphertext of the encryption scheme Pi1 or Pi CPA. So the ciphertext space is not changed, so it is CCPA only. Is this clear?
Yes, ma'am.
Okay, here comes the padding oracle attack. So which of the following is or are correct? Padding oracle attack is performed to break authenticated encryption scheme constructed using encrypt then authenticate approach. Is it true or false? So for encrypt then authenticate approach, we already had seen that if we have a CPA secure encryption scheme and we have a CMA secure MAC, then the encrypt then authenticate approach actually gives an authenticated encryption scheme. So you cannot mount padding oracle attack on that. So this is wrong. Okay, this is wrong. Padding oracle attack is performed to break authenticated encryption scheme constructed using authenticate then encrypt approach. This is actually true. We will come to what padding oracle attack is for quick recap. Last option says padding oracle attack is capable of recovering number of padded bytes in the messages. It is true. We will see how. And padding oracle attack can be used to retrieve the whole plaintext block. This is also true. So let's just recapitulate what happens in the CPC mode of encryption and how we can exploit the padding notification from the decryption side to actually retrieve the whole plaintext block. So let's say we have two message block M1 and M2. And how does the CBC mode of encryption work? So there is this initialization vector, and you get the block cipher FK. So your first this IP is XORed with your message, and the output is C1, and then it gets XORed with M2, passes through FK, produces C2. So IP C1 C2 is your ciphertext for message M1, M2. Now in the padding oracle attack, so for that we need the padding. So how the padding is done? Let's say we consider L bit block. Okay, each block has size L bit. Now or let's talk in bytes. So let's say each of the block has length L bytes. Now if the last block has actually length less than L bytes, so we append some number of bytes to make it a total of L bytes in the last block. So let's say your L is 8, and if you have the last block size 5, okay, you have some content here, but it has size 5 bytes, but your each message block is supposed to be 8 byte of length. Then you add 3 more bytes, each containing the value of 3, that is the number of extra blocks. So you have 5 bytes, you need 3 more bytes to make it a whole 8 byte length block. So you actually put the byte representation of 3 in the last 3 block. So if B is the number of bytes required to be padded in the last block, we write that this is the content, and there you append B number of blocks, B bytes, each byte containing the byte representation of the value B. That is how padding is done in PKCS 5 convention. Then now you can exploit this structure. So whenever this decryption is happening over a ciphertext, so you can actually exploit the decryption oracle. So when let's say C1 is corrupted, okay, so what happens is that your FK inverse C2 XOR with C1 is supposed to give back the value of M2, but you change some bit in C1, then corresponding bit of M2 also gets changed, right? So the change in C1, that is the previous block of the last block, gets reflected in the value of the last retrieved plain block, which may have padding in it. Now the oracle attack, padding oracle attack, happens in this way. First you start to corrupt or occur some do some bit flip in the first byte of this ciphertext component C1, okay, the previous block of the last padded block. So you change the first byte of C1, then first byte of M2 will get affected, and if this first block of M2 is actually a part of padding, so while decrypting or while discarding the padding, you actually read the last block value, which is B, and then you continue to drop B number of blocks, ensuring that each of them containing the value B. If it is not the case, so if you found that let's say 3 was appended here, right, to pad a 5 byte block, you added 3 more byte, each containing the value of 3. Now if it would happen that this is value 2 and then these are value 3, So while dropping off the padding, you read the last byte value to be 3. So you know that there are 3 bytes that I need to discard from the padded message. So you discard this, you read this value to be 3, you discard this, but here you are supposed to read the value to be 3 but you find it to be 2. That means something wrong happened, and you raise a padding oracle error here. Padding, you say that it's a bad padding. Now if an adversary is manually tweaking the ciphertext while sending the while exploiting the decryption oracle service, then it is actually corrupting the first byte of C1, so that first byte of M2 gets corrupted. Now if first byte of M2 is also part of padding, then the padding will be wrong in that case and it will throw a bad padding error. This will imply that all the L bytes of the last block M2 are actually part of padding block. So this whole block is actually a padding block. So you know the length of the padding bytes to be L. What if it does not throw the bad padding error with the corrupted first byte of C1? Then you know that first byte, although it is affected, but it is not the part of padding. That is why bad padding error did not come. So you try with corrupting second byte of C1, so that second byte of M2 gets affected, and check whether second byte of M2 is part of the padding bytes or not. Like that, you eventually, with the leftmost index where you get to see a bad padding error, you know that that is the number of padded byte in that final block of message. And after retrieving that information, you can even gradually retrieve the actual content of other bytes in that last plain message block one after another, and then your CCA security is gone, right? So yes, that is how your padding oracle attack can actually break authenticated encryption scheme, by breaking the CCA security using the padding oracle attack in the CBC mode of encryption, right? Okay. Select the correct statements. In a key exchange protocol, the adversary should not be able to guess the key computed by both the parties at the end of the protocol except with negligible probability, even after seeing the transcript. This is called weak privacy. This is correct, right? So I was already telling that in a key exchange protocol, at the end of the protocol, both the sender and receiver agrees upon some key. By the correctness of the scheme, both sender and receiver should agree upon the same value of the key k, and even after seeing the communication between the sender and the receiver, which is called the transcript, an outside adversary, after seeing the transcript, should not be able to guess the correct value of the key upon which both the sender and receiver agree upon. That is the concept of weak privacy. And in a stronger notion of privacy, we say that not only it is hard to guess the exact value of the key by seeing the transcript, it is also hard to distinguish the value of the key from a uniform random element of the key space. That is the stronger notion of privacy. So both the statements are actually correct here. In abstract Diffie-Hellman key exchange protocol, both sender and receiver have some randomly chosen value alpha beta respectively. E is a function such that values of E alpha, E beta are communicated through the public channel. The final output, that is the key of the key exchange protocol, is f of alpha comma beta. Then choose the correct statements. So I will wait for 2 minutes. You can give the answer. So this is the abstraction of Diffie-Hellman key exchange protocol. without really specifying the instantiation of the function e and f. Anyone?
One and two are correct.
1 is correct, 2 is correct. Third statement is wrong, right? And fourth is also wrong. Yes, you are correct. So that is the required property of Diffie-Hellman exchange protocol, because what usually happens is that there is sender, there is receiver, and it has its own secret, say alpha, chosen, and instead of sending alpha in its raw form, it actually computes f of alpha and sends the value f of alpha to receiver, and the receiver also computes some samples some secret value beta on its own, and instead of sending the secret value beta through the public channel, it computes f of this function is named e here, so this is e, so it computes e of beta and sends e of beta to the public channel. Now e function should be such that given alpha it is easy to compute e of alpha, but given e of alpha it is hard to compute alpha. That is the necessary property here. And so receiver gets e of alpha here and sender gets e of beta here, and now with e of beta it somehow combines alpha and e of beta through some function so that it can generate f of alpha comma beta, and here also it gets the e of alpha value from sender, so using the e of alpha value and its own secret beta, it somehow combines them to get f of alpha comma beta, so to agree upon a common random key. So yes, that is why this is correct. It should be of course easy to compute for both sender and receiver. However, the outside third party adversary who is seeing the transcript, so transcript consists of e of alpha and e of beta, and from e of alpha and e of beta it should not be able to compute f of alpha comma beta, otherwise the whole purpose of key exchange protocol is nullified, right? So also as I already said, from e of alpha it should be hard to compute alpha, otherwise by seeing the transcript only the adversary could know the value of alpha and beta easily and then compute f of alpha beta on its own to get the value of the secret key. So this should not be the case, so that is why this is wrong and this is wrong. These two are correct. This is question on one-way function, one-way trapdoor function. You can answer. Says that one-way function is easy to be evaluated on some random input x from its domain, but given some random value y from its codomain, it is hard to invert. This is true, right? That is the definition of one-way function. So this is true. A one-way trapdoor function is easily evaluated on some random input x from its domain, and given some random value y from its codomain, it is easy to invert with the knowledge of trapdoor function. So this is how one-way trapdoor function is defined. So this is also correct. If a one-way trapdoor function with chain f and inverse algorithm is defined over x comma y, the function f is deterministic 1 to 1 and on to. Well, it is deterministic. It should be 1 to 1, but on to it's not necessary. It can be many to one function, right? So 1 to 1 is necessary because by during inversion there should not be any ambiguity. From y you should come back to x, so it is 1 to 1, but on to is not required. It is required when we talk about trapdoor permutation. There determinism 1 to 1 and on to, all the three properties are required. Okay, so I think can stop here. And about the I think there is the doubt on Markle tree, so we can get back about that in the next session, next Saturday. Okay, so thank you for attending.